We're going to talk today about sieving without sieves with Dr. Jeff Bodycomb leading the discussion. Please go ahead and begin, Jeff.
Great. Well, thank you very much. One quick comment, if you have questions during the presentation, go ahead and type them into the chat box. And if I spot it in time, I will try to answer as I'm talking. Or you can ask questions at the end or contact us after the webinar. So today I'm going to give a quick argument for particle analysis. And then I'm going to start talking about sieving. And then talking about sieve replacement with image analysis and a cam sizer. And really, that's the reason behind the title of Sieving Without Sieves is that you can use image analysis to avoid working with sieves and their headaches. So really, what's the motivation, or why are we measuring particle size? And we're measuring particle size because particle size is connected with a lot of final properties of your final product. And so you want to make sure that the properties you measure match what you need in order to get the performance you want. I'll give you two quick and easy examples. The first is coffee. As you change the particle size, you're going to change the taste properties. If you have coarsely ground coffee, you'll have a watery cup of coffee. So you can think of the extreme of just coffee beans. They're not going to do much for you in terms of flavor. If the coffee is too finely ground, you'll extract more than you want, so you have too many aromatics, acids, and bittering agents. The filters could be blocked, or you could have the fines go through the filter and into the coffee cup. Another example where the need for particle sizing is quite obvious is in any abrasive, but I'll mention sandpaper. And if you have the wrong size or the wrong grit, you'll have the wrong surface finish. So if you pick something that is a coarser grit than you want, your surface will be overly rough. And if it's too fine a grit, you'll have a very smooth surface, which will quite likely take you a long time and may not be your target. If your size distribution is too wide, you'll start seeing grooves and rills, particularly you'll see those on your surface. So today I'm going to talk about two measuring systems. First is sieve analysis, which has a size range. I want to talk about two different measuring systems. First is sieve analysis, which has a size range of about 20 microns to about 30 millimeters. And then I'm going to talk about the cam sizer, which also has a size range of about 20 microns to about, exactly 20 microns to 30 millimeters. So let's start with sieving. Sieving is a very traditional measurement. You mentioned the size range. Some advantages of sieving is that you get statistics in a short time. You can measure a lot of particles quite quickly. Older optical systems, you did have that problem with measuring enough particles. And sieving really works because you'll have your particles on a screen as shown on the left, and anything that is finer than the holes will go through. Anything coarser will stay on top. And so you have sieves, you stack them up, you'll shake the stack, and you'll find out how much sits on each sieve. So really, when you think about a particle measurement, you have to ask yourself, what exactly am I measuring? And in sieving, you're really saying what size particle passes through a two-dimensional and typically square hole, as shown by the wires on the left. So if you're measuring spheres, then you'll see the diameter of the sphere. If you're measuring sticks, you will probably see the diameter, or rods, you'll see the diameter of the rod, but you will not see the length. And so I recently had a customer that could sieve long rods and short rods, and they would both wind up on the same sieve, and so that they couldn't tell which ones were longer or not. And if you're sieving coins, you'll find, again, diameter of the thin coin. There are surprises. So I talked about spheres. I mentioned this in the earlier slide. So I have a sphere. I look at the diameter. Great. Okay, I have all my spheres, that diameter sitting on the right sieve. But if I have doublets, so if you have spheres and you're spray drying them and two of them glue themselves together because of a process issue, you'll find out that the doublet winds up on the same sieve as the sphere of the same size. So you really can't tell when you have this kind of event in your process. Sometimes you're lucky and it doesn't matter. Sometimes you're not so lucky and it does matter. Another example are lenticular particles. So if you think about things that look like lenses, there is no single simple dimension that tells you how that's going to fit through the sieve. You can't just take the diameter or the thickness. You really have to find the stretch from here to here. So as long as you keep this in mind and really keep this kind of fact in mind, as you go to compare particle analysis techniques, you can stay out of trouble. So there are standards for sieving, and if you look at them, you're going to find out that you need to test both the sieve shaker and the sieves, and you have to monitor their performance. And so there are a few ways to do that. You can look at the sieves with a camera. You can test particles through the sieve. One thing to keep in mind as you look at these sieves is the tolerance on the mean size. So we have a mesh width W here, and that mesh width can vary by some amount within the same sieve. The workflow, which really starts much like every other particle analysis technique. You start by sampling, drawing out a representative sample of your particles, which is often much less convenient than you wish. You would then divide that sample down into a smaller quantity, ideally with some sort of sample splitter. You then put the material onto this onto your sieve stack. You shake, you evaluate the results, and then you clean everything up for the next measurement. So here's a schematic of what really happens mechanically. You add a known mass of sample to the top of a sieve stack. So here I put 150 grams of material on the top sieve. I shake and tap with my sieve shaker, and so that allows the smaller particles to move down until they find the sieve with the screen size that's smaller than the particle, and that's where it sits. I then take each screen off of the stack and weigh the particle fraction on each screen. And so I'll take each one off and do an individual weighing. Next, I analyze the data. And finally, I do the dishes. I clean the sieves for the next user. Unfortunately, this is not like cleaning ceramic dishes where you can kind of chuck them in the dishwasher, rub them down with a brush or whatever to make them clean. It's sieves are fairly delicate beasts, and you don't want to change the hole sizes, which makes washing a whole new adventure. So let's take a visualization of the results. And so I have off of each sieve, I'm going to determine the mass of material. So I have 4.5 grams in the pan, then 6 grams, and 15, 30, and so on up. So I'll know the total mass is 150 grams, and I will divide or define the percentage of particles on each pan. And that's represented by the blue bars and the left axis, which is given as volume or mass. The bottom axis is particle size. I can then start to add these up in order to find the cumulative size distribution. The next is, how do I find the differential size distribution, or the peaks that some people like to use? And really, by taking the mass of material in each pan and dropping it to the bottom of the graph, I can say how much material is in each pan. I can find my modal size value, if you wish. Now notice that these bars are quite fat, and I'll mention that later on, but really there's a pretty hard limit in the number of pans you can put on a sieve stack before things get unwieldy. In this case, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. To find the particle size, or to learn about the distribution, I'm going to say, well, at 250 microns, I have, and that's that green arrow here, I look on my left axis, I see 36% of my particles are less than 250 microns. If I move on up and I want to find what is D50, I'm going to interpolate between these two red dots. And so on the left axis I find 50%, I move over, I look down, I find 330 microns as the particle size. Well, that doesn't seem too bad, but there are some practical difficulties. On the left it's a bit difficult to see, but we have a lab that's doing the analysis, and they have the scale and they have their other analytical balance below the air conditioner. It's a little tough to see. In the top picture you can see a sieve that is just full of particles stuck to it, and this leads to cross-contamination. The user was not getting the particles out of the screen. Fortunately, they were not beating on the screen, which can make creates other problems. So anyway, you have this cross-contamination issue. Probably needs to go in ultrasound bath for a while. As you go to weigh the material, well, this is okay. I have 4.7 grams of material coming off of one screen. But I think this was the pan for this particular sample. It shows 0 grams. Well, if I move this amount of material over to a balance with higher resolution, I see 0.7 grams. So anyway, what you see in this is that there's a number of ways that these kinds of measurements can go wrong, and it requires a fair amount of operator skill and alertness to make sure everything goes well. So what about these tolerances of mesh width that I mentioned before? So let's say I want to find D40. At 40%, I have 63 microns, and I have plus minus 3.7 microns. Well, if I go 63 to 66.7, now I go from D40 to D44%. If I go down, I go D36, with 36% of my particles. So this tolerance on the mesh, which really shows up in the x-axis here, can lead to quite dramatic results when you start looking for things like D50 or the volume. So the fraction of particles with a size a size for which half the particles are smaller. Okay, well, sieves are always full of surprises. So here is a measurement of the diameter of some spherical particles shown in the green and blue. And in a few slides I'll get to how we did that measurement. And then here is the result of sieving, and those are the little brown stars, and using the nominal sieve sizes. Now I mentioned these are spherical particles, so you say, okay, well, the one place where everything seems to match in particle analysis is when you're measuring spherical particles. And it doesn't match very well at all. So what happened and why? Quick hint is at the bottom of the slide. I'll jump to the answer. It's the tolerance in the mesh width. So here's an example, and this is for the this is for the 1400 micron mesh. We see a distribution of widths, and so horizontal width and vertical width, if you will. And you can see that actually some of the holes are larger than the modal size sieve hole. So what that means is that these particles, if they're round and they find a hole through which they don't fit, they're going to move over to find a hole through which they do fit. So this particle just slides up and to the right and drops through the bigger hole and moves down the stack. Now this is a pretty nice set of sieves because the data actually reported all these distributions. When I go and feed in the real mesh sizes, taken as the upper size of the holes, then the results of the two analyses match very nicely. So you can see the data points, which are the stars, shown here, line up very nicely with the optically measured diameter of the spheres. Well, that's not the only irritating thing that particles can do. They not only just find the largest holes that they can also get stuck in sieves. So if you think about round particles and you are shaking a sieve up and down, the screen is going to flex up and down. And so when it flexes up, the holes will get a little bit larger. Or there'll be some motion, so there'll be sliding friction. So the sphere will start to slide into the hole, which then tightens during the next cycle, and then it gets stuck. And so you will have a problem deciding what to do with these particles, and you'll have a problem cleaning out your sieve. People get around this trying to use sieving aids. You can see the chain at the bottom, and that's supposed to help force particles down through the screens. Well, if you escape all that, you get to think about the variations in shaking amplitude. So if you're using a device to shake your sieve stack, and most people do, you decide, well, what am I going to do? Well, if you want to shake something, just turn it up as high as you can. So just put it right up to 11 and go. That doesn't actually work so well. This is quartz sand with a 2-minute sieving time. With the amplitude of 2, I can see the blue line. Amplitude of 1, it's the green line, and 0.5 is the red. And actually, you expect that the green is the best because you have the most fines. The trouble is that green is in between the high amplitude and low amplitude. So you have to kind of find the right value for shaking amplitude. So method development is not as trivial as it might first seem. Now, you are beating your sieves with particles during sieve analysis. So if you take the example of sand, and if you put your car in a box with sand and start shaking the sand over your car, you will take your car out and find out you have no paint job left. That's roughly what's happening to your sieves every time you do a sieving. So if you do sievings, particularly with harder particles, or if you're careless with cleaning, you're going to start to wear out your sieve. You're going to start pushing wires around. You might wear some holes larger. And so this requires another step of work in order to monitor sieve condition. And this can go back to doing something like using particles with known sizes to check sieve performance or optical techniques. So this is a photograph of a particularly worn out sieve. You can see the holes are all different sizes, and they've even gotten different shape holes now, little trapezoids. Now sieving has some advantages, and I haven't gone into too much of it, although I've implied a lot of it, I hope. It's robust and industrial suited. You can hand a sieve to somebody and they'll have a pretty good sense of how to get started. And they are not, they don't need a temperature controlled environment. They don't need to be kept away from dust that doesn't bother your analysis and so on. The handling's pretty easy. They don't need to be plugged in. If it gets too cold, they don't care. If it's a little bit humid, they don't care. There's an immense history of sieving data. And if you're trying to run a stable manufacturing process and you have this entire history of what caused what, you really don't want to give that up. And at fairly low initial cost. Sieving does have disadvantages, particularly as you start pushing your process. It has a fairly low resolution, so there's a small number of size classes that you can use in a single sieving measurement. You have a limited sample amount. I didn't get into that, but you really need to have enough material that you can weigh and not so much material that you start to overload or blind your sieves. Your operation costs can climb because you're going to need a fair amount of labor, and you're going to find out that this wants to be skilled labor. you're going to need to spend money to replace the sieves and monitor their condition, because it's hard to confirm correct sieving operation. For some size parameters, you really can't see what has changed in your material. And so, for example, if you're worried about doublets and you have spherical particles, which looks like the easiest problem in the world, sieving is not going to do the job. And I was just at a customer a couple weeks ago where they were looking for the doublets and realized that they went right through the sieve and had to use image analysis. And there was no shape analysis possible. And this is a great segue into what I want to introduce, which is dynamic image analysis. And dynamic image analysis is a technique of taking pictures of particles to extract particle size. The particles flow through the measurement volume of the instrument and the field of view of the camera. So I have these particles in the lower right dropping and the camera on the right taking pictures. There are no other moving parts. The particles fall, you take a lot of pictures, and you're done. You can get a lot of particle images very quickly, and in part that's due to lack of moving parts. And particles are projected in random orientation, 3 dimensions. That's something important to keep in mind as we talk about some of the vagaries of image analysis. You can actually orient the particles, which is done in certain special cases. Data analysis, which I will go through fairly quickly. You get a good raw image. You start with a good raw image, everything becomes easy. You binarize to black and white, find your particle images, analyze each particle, and output the size distribution. Image analysis lets us ask, once again, what size? Different measurement systems provide different results. There are lots of size measures that you're allowed to do once you have a photo. One is to look at the area, or called X area, which is the diameter of a disk with the same area as your particle image. So that would correspond to treating it like a sphere. You look at XC min, which is effectively the width of the particle. And this is best suited for comparison with Sieves. Or you can look at the Ferri max, which tells you the length of the particle, which is suited for comparison with other microscopy efforts. And incidentally, that is how you can go and look at things like the length of rods or doublets and so on. As an aside, and I think I mentioned this once more, shape parameters can be calculated. So you can take ratio of the area to the perimeter. You can take a ratio of the width to the length to find an aspect ratio, and so on. Quick comment on size definitions. And I plot the volume on the left and the particle size on the bottom. And in red, I put XC min, X area, and Ferri max in blue. This is the same data set, same set of pictures, same treatment, 3 different size definitions, 3 different particle size distributions. So it's important, like in all particle analysis, that you communicate exactly what you mean when you talk about particle size, because you'll get different answers if you use different definitions. Image analysis is extremely reproducible. As you can imagine, we are dropping particles in front of the camera and taking pictures. If you take the picture of something twice, you tend to wind up with the same picture. And this statement is even made stronger when you look at populations, as long as you meet some limits which are met quite nicely with the camsizer. Do you look at enough particles? And so on. And so this is actually 8 measurements of 4 different samples. You can see the curves overlay just about completely in all 4 cases. So how do we get at sieving? Well, you might start with area. It seems like a natural choice for microscopy for a couple of technical reasons. And here I plot volume on the left as a function of particle size, and you can see the black line with the stars as corresponding to the sieving result, and the red as the dynamic image result. And the results are not good. Now let's look at XC min, or the particle width. volume on the left, particle size on the bottom. Again, the black stars are the sieving results, and the red is the image analysis. And here you see that the results are extremely close from the very beginning with no further effort on our part. So that clearly is the way to go. A couple things to, asides. I showed you a picture with a size range of 200 to 2,000 microns. So that's only a factor of 10. How are you going to cover a wider range of sizes or different size products? So if you have a material where you are interested in finding out the dust as well as the overs, you're going to need a wider size range, or you're going to have pretty good analysis for that wider size range. The way we do that with the cam sizer is with two cameras. We have a zoom camera and a basic camera. The zoom camera is, like the name implies, zooms in on the particles. The basic camera takes a wide field of view. And what does this mean? Small particles with high resolution from the zoom, and large particles because of the wide field of view for the basic. And they both share a field of view, which makes knitting the data together quite easy. Calibration. There are a few ways to calibrate your sieves. One is to use a master sieve stack, which I kind of sketch out as the golden stack. Unfortunately, that wears with use. So you want to take these sieves and use them every once in a while to check your normal sieve stack. The other would be to use calibration beads or optical techniques to see what is happening to the mesh of your sieves. This is time consuming, and it's not something you want to do all the time. If you use a master sieve stack, in fact, you can't, because you'll beat up your master sieves. With an optical technique, we can use a calibration reticle. Here's a photograph of the one in the cam sizer, and it just has pictures of particles. They're round particles, and there's some technical reasons why that makes for better calibration. They're traceable to international standard, covers the entire measurement range, gives you good instrument-to-instrument agreement, and does not wear, because this only interacts with light. Another advantage to image analysis is resolution. So I've been showing some sieve data before, and you see the lines between the points as straight lines. Say, oh, well look, right here at 1.25, they're two different numbers. Well, this is really just a straight line drawn from the sieve data at 1 millimeter up to 1.6 millimeters or so. Whereas in the red, we have all the individual size bins. And really that's because we're taking pictures of each particle, and so in the computer we have all the data for all the particles, and we can make as many bins as we want. So I talked a bit about spheres, and if you've been in particle analysis, you know that as soon as you move away from spherical particles, techniques stop agreeing quite so nicely. So here are some lenticular particles, and the black stars are the sieving results, and the red is the cam sizer result. This is volume on the left and particle size on the bottom. So what's going on here? Well, there are a few things that are happening. The first is that the particles that we measure in the cam sizer tend to tumble by image analysis. And meanwhile, in the sieve, we're going to assume that the particles will bounce around until they fit through the sieve mesh in the optimal direction for getting through. Once we extract sizes from the cam sizer, generally XC min, you might argue, hey, we can take the Ferrier max in order to find the long length of this. It still doesn't work so well because there's no single simple measure or obvious measure of the size of a lens-like particle that's going to fit through a mesh. You have to sit down with some geometry to start figuring out several different lengths and what fits. Okay, well, so now I've gotten you worried about lenses. I'm going to keep going on a roll and make you worry about other particles. So if you have angular particles, things like coal, sand, sugar, again I plot volume on the left as a function of particle size. I have the black stars from sieving data and the red line from the cam sizer. And you can see, once again, there's a pretty systematic difference between the two results. And if you recall, I did not show an exact match when I said the XCmin was the best fit. So what could be happening here? Well, the size measured by the sieve for a cube, because that's conceptually easy, is going to be the length distance between the flats on the cube. And if I do XCmin in the cam sizer, I'm going to get some projections which give me a small number and some projections that give me a larger number. And so there is a difference between the techniques. Okay, so here I show the size of the sieve in the red and an XMin on the cam sizer. So that works quite nicely here, and it's not going to quite work so well as I move up here. So we still need to do some kind of fitting as a final adjustment. So I need to find a way to move my angular particles over. And so there is a what we call Q3. It's kind of a quick and dirty volume-based fit where I can shift the data over to make it match up with the sieving results. Now there is a limit to this quick and dirty approach, which is shown by these two samples in green and red. So left side I have one fitting set, and the green fits quite nicely, and the red stars do not fit the smoother cam sizer results very well. But if I do a fitting so that the red stars fit, the green doesn't fit perfectly. Now in some processes this fit is quite close enough, but we can do better, so we will. And what we really need to do is what we call elementary fitting. And we call it that because we're fitting one element up. We're using one element of the distribution as an adjustment in order to understand what's happening. If I do that, then both distributions will fit the sieve data quite nicely. And so I can have a correlation I can keep using on future measurements and tie back to my past sieve results. So really the use case is here I have a differential size distribution of green and red samples with a different width of distribution but with similar shape. So here I plot volume as a function of aspect ratio. And that's something you can go and measure by image analysis that you cannot determine with sieving. Concept: I have data from the entire sieve stack and compare to the image analysis results, and I have data from a single sieve and I compare to the image result. And when I say I compare, I actually don't do anything. I put all the numbers in the computer and let the computer worry about it. So basically I'll take a measurement with the cam sizer, and that goes here, this bottom left list. I take the measurement of a single part of the sieve stack, so I'll take this sieve out and measure it all by itself, and it goes in the top. And then I type in the results of my sieve measurement. I press the the OK button, and then I will have a fitting file, and so that will let me go back and connect my sieving and image analysis data, and will also let me extract shape information. I can avoid washing dishes. I can get my results much more quickly. So generally it makes life more fun until my boss realizes that I can go off and do something much more useful than wash dishes. So you can fit, with a single fitting file, you can fit samples with similar shape and different width of distribution or even multimodal distributions as long as the shape is roughly the same. So if it's coming off of the same process, you're doing pretty well. Now, if you have varying particle shape, and so if you have abrasives and you have some that are more cubic and some that others that are more needle-like, you will need different fitting files for each kind of product. But these fitting files are fairly easy to create. So, as some concluding comments, The cam sizer can be used in place of sieves to provide fast, easy data. It also provides shape data. Historical sieve data can be matched to an elementary fitting process, and this requires really one good sieving measurement and 2 cam sizer measurements. So it's pretty quick. So image analysis advantages. Sieves tend to be low resolution, cam sizer higher resolution, limited sample amount on a sieve, flexible sample amount on the cam sizer, no shape information for your sieving, with shape information for the cam sizer, high labor costs with the sieve, particularly as you babysit these sieves, lower labor costs with the cam sizer. Basically, if you have a method, you dump it in, you press the go button, and you collect the printout. Hard to check sieve accuracy. It's trivial to check cam sizer accuracy with the reticle. You can't see things like length of rods or doublets in the sieve analysis, but you can with the image analysis. Okay, I think it's time to open the floor to questions, which feel free to go ahead and type your questions into the chat box. Or if you think of the questions later, you can email me at jeff.bodycomb@horiba.com or at labinfo@horiba.com. And these slides will be on our website, and if you visit our download center, start at horiba.com/us/particle, you can find all sorts of other particle analysis information.